Yeah, I guess we can start. So, hello, everyone. Welcome to, I think it's the 6th session of the category theory seminar at Stellenbosch University. Today we're going to be listening to Elena talking about principal bundles over arbitrary sites, I think, and some more. Thank you.
Okay, you can see the slides. Yes. So, first of all, thank you very much for giving me the opportunity to speak, and I hope I'll be seeing you there soon. The talk will be about my PhD project, which is about generalizations of principal bundles and quotient stacks in categorical contexts. In particular, we will see how to generalize these notions to the context of sites, so categories endowed with the Grothendieck topology, and then to the context of bisites, which will be a two-dimensional version of the story. Let's start by, oh, I cannot change slide. Well, okay. Can you see the new slide? Yes?
Yes.
Okay. So let's start with the classical case. So principal bundles over topological spaces. If we have a topological space Y and a topological group G that acts on it, a principal G bundle will be another topological space, P, with an action of the topological group on it, and the G equivariant continuous map from P to Y that is also locally trivial. This means that we can find an open covering of the codomain, so of Y, such that every time we restrict to this open covering, what we get is trivial. So we get a projection from a product into the second component. And this notion is very important in geometry. There are different flavors of it. So we can do the same thing for schemes, for example, or for manifolds. And among the various things that are done with principal bundles, one is that we are able to construct quotient stacks explicitly using principal bundles. And the idea is that the quotient stack sends a topological space into a group of pairs of principal bundles equipped with a G equivariant continuous map into X, which is a fixed topological space. And these objects are important because if we, for example, consider the case in which X is just a point, so a topological space given just a point, what we get is the classifying stack, which allows to compute cohomology groups. And so it's very useful in geometry. So what we are going to do is we are going to generalize these concepts in a categorical way. And in particular, to generalize the notion of principal bundle, we'll need to replace the concepts in blue with categorical counterparts of them. But before doing this, let's recall what a site, so that we have our setting. So we take a category C with pullbacks. We say that the sieve on an object of the category is a collection of morphisms that all have C as codomain and is closed under precomposition. And an alternative way to see it is as a subfunctor of Yoneda of C, so a natural transformation with injective components that has Yoneda of C as target. And once we have sieves, we define a Grothendieck topology as an assignment for every object in the category of a collection of sieves that are called covering sieves. And this needs to satisfy some axioms that are just saying, the first is saying that the maximal sieve is a covering sieve. The second is saying that being a covering sieve is closed under pullbacks. And the third is saying that being a covering sieve can be checked locally. And we also have a notion of a basis for a Grothendieck topology, like what happens for a usual topology. So instead of talking about sieves, a basis speaks about covering families. So we don't require the covering families to be closed under pullbacks. We don't require the covering families to be closed under precomposition, but we still require these some axioms that are really similar to these ones. And the idea is that once we have a basis for a Grothendieck topology, we can generate the whole topology just by closing under precomposition. And we will sometimes use this notion of basis instead of the notion of topology, but the two languages are equivalent. And the basic example of Grothendieck topology is that of the category of opens of a topological space. So if we have a topological space X, we can construct a category that has as objects the open subsets of the space, and as morphisms just inclusions between them. And we can endow this category with a Grothendieck topology that is called the standard Grothendieck topology. And we simply take as covering families the open coverings of the topological space. And this gives us an idea of why we call this thing a topology. And this is the example 0, we can say. And we can also make a global version out of this kind of topology. So we can endow the category of topological spaces with a standard topology in which, again, the covering families are the usual open coverings. And we'll see that this is what will recover the classical case of principal bundles in our theory. So if you remember the blue concepts, the first one was topological group. So we need to replace a topological group with a categorical counterpart. And the most natural thing to do is to take an internal. So we have our site, so our category with a Grothendieck topology on it, and we take G an internal group. So it will be an object of the category that behaves like a group. So it has an internal multiplication, an internal neutral element, and it satisfies some categorified group-like axioms. And now we need to define what it means for a morphism to be locally trivial. And the idea is that we want to use the Grothendieck topology to do so. So we say that a morphism in the category is locally trivial if we can find the covering family of the codomain such that every time we pull the morphism back along a morphism of the covering family, what we get is trivial. So it is isomorphic to a product. And if you look at this definition and think about it in the case of topological spaces with the standard topology, what we get is that here the FIs are just inclusions. And so every time we compute the pullback, this is the same thing as computing a restriction. And so we get the classical definition that we saw at the beginning of the talk. And now that we have a notion of locally trivial morphism, it's very natural to define a principal G bundle over an object of the category as another object that has an action of the fixed internal group on it, and the G equivalent locally trivial morphism, pi p, like this one. And then we define morphisms of principal bundles just as morphisms in the slice category that are also G equivalent. So they respect the actions of G that we are fixing. And a very important property that we are able to prove is that principal G bundles are closed under pullbacks. And the reason of this is that the Grothendieck topology is closed under pullbacks. And so this is what allows us to prove this result. And this property will be very important for us because it is what allows us to construct quotient prestacks. So what we do is we perform the same construction that we saw at the beginning for topological spaces, but for a generic site. So we fixed an object X of the site, and then for every object Y, X over G will send Y into a category of principal bundles or equipped with a G equivariant morphism into the object X. And then we need to define the assignment of morphisms, and what we do is we define it via pullback along the morphism. And so the fact that principal bundles are closed under pullbacks allows us to show that this is a well-defined object. And moreover, this is a pseudo-functor, and so it is a prestack, what we call a prestack. And this is due essentially to the fact that the pullback is pseudo-functorial. And now, since in the classical case, the quotient prestacks are always stacks, we want to see whether this is the case also in this categorical context. So we want to see whether these objects satisfy some gluing conditions. But before doing so, let me recall the definition of stack, in case maybe not all of you are familiar with it. So a stack is a two-dimensional version of a sheaf, so it will still glue objects and morphism, but it will glue objects in a weaker way than what we are used to for a sheaf. And so to introduce this weaker gluing condition, what we need is the ingredient of a descent datum. So if we have a pseudo-functor f from C up into cat, and the sieve on an object T, a descent datum on the sieve for f assigns to every morphism in the sieve an object, WF, which is in the image of the domain of the morphism. And so we can think of it as a local object. And then this assignment needs to be compatible with respect to composition. So every time we have a chain of morphisms, G and then F, where F is in the sieve, we have that the assignment on the composite F composed with G needs to be isomorphic to the assignment, to the descent along G of the assignment for F. And moreover, these isomorphisms need to be compatible with respect to composition as well. So we have these, if we have a chain of free morphisms, we have this condition, this commutativity that is called the cocycle condition that relates all the isomorphisms that we have in play in this situation. It's not so important, but it's just a coherence condition for these isomorphisms. And once we have a descent datum, we say that it is effective if we can find an object, W, this time in the image of C, which was the object for which S is a sieve. So W can be thought of as a global object instead. And the idea is that W allows to recover all the local objects assigned by the descent datum. So for every morphism F in the sieve, WF is homomorphic to F star W. And again, we also have a coherence condition satisfied by these isomorphs with respect to composition. That is not really important. So we say that a pseudo-functor is a stack if every descent datum on a covering sieve for it is effective. So we have this gluing condition on objects that is true only up to isomorphism, as we saw in the definition of effectiveness. And then we have that F needs to be a sheaf on morphisms. So it has to glue morphisms on the nose. So the idea is that if we have two objects in F of C, and then for every morphism in S, we have this morphism WF, from f star x to f star y, and these WF are compatible with respect to composition, then we can glue them together to get a global morphism W from X to Y that recovers all the local ones. So F star W is W of F for every F. And then this gluing needs to be unique in the sense that if we now have two morphisms, W and W prime, that agree locally, so F star W is equal to F star W prime for every F in the sieve, then they are equal. And these two conditions are exactly saying that F is a sheaf on morphisms. Okay, so now that we have the definition of stack, we are going to see a characterization of it that will be useful later on in the talk. So Street proved that F is a stack if and only if for every covering sieve, the functor of precomposition with the covering sieve is an equivalence of categories. And the idea behind this characterization is that the left hand side here is equivalent to f of c by the Yoneda lemma, while the right hand side is a category of the same data, essentially. And the idea is that the three conditions of equivalence of categories, so essential surjectivity, fullness, and faithfulness, correspond to these three gluing conditions that we saw before for a stack. And we'll see why this characterization is useful for us. So now, as I said, I wanted to see whether these quotient prestacks in this categorical context satisfy some gluing conditions. And it turns out that if the category C is nice enough and the topology is subcanonical, then they are stacks indeed. And the proof of this fact is not as easy as the classical case, because in the classical case, the topology is very well behaved and very easy to handle. While here in this general context, it is not. So there are different ideas behind the proof, but the most important one is that we use the fact that in a subcanonical site, and subcanonical means that every representable is a sheaf, then every object can be seen as the co-limit of every covering sieve over it. And this is just a well-known fact, but is very crucial for the proof. And now what we want to do is we want to write the same story, but in dimension 2, so for a 2 category instead. So our setting here will be a 2-1 category. Some of the things I'm going to say can be done in general for a 2 category, but we'll need the 2 cells to be invertible in order to construct quotient prestacks. So I'm just taking this hypothesis from the beginning. And now we want to have a topology on this 2-1 category. And sometimes in the literature, when one wants a topology on a 2 category, they just consider a topology on the underlying category. But this was not good for our purposes because we really need a topology that is 2-dimensional in nature. And so what I did is I decided to use the notion of bitopology defined by Street for a bicategory. And this notion of bitopology is very similar to the usual notion of topology. The only difference is that instead of being closed under pullbacks, it is closed under isocomma objects that are a 2-dimensional version of the pullback. They are sometimes also called bipullbacks. And so this is the only difference. And then we again need to replace all the concepts that were in blue in the first slide in this 2 categorical context. So first of all, instead of an internal group, we now take an internal two group. So this is just a two-dimensional version of an internal group for which we don't have commutative squares, but we have coherent isomorphisms expressing the group-like axioms. And then for an internal two group, we can still define what is an action, and we can still define what is a G-equivalent morphism. And the idea is just that instead of having a commutative square, we have a coherent two set. And so again, it is easy to define what a two locally trivial morphism is. So we say that G is two locally trivial if we can find a covering by sieve such that every time we compute the isocomma object, this time of G along a morphism in the sieve, what we get is equivalent to a product. So the idea again is just that we upgrade pullback with isocomma object and everything still works. And so now we can define what principal G2 bundles is just by saying that we have a G equivariant to locally trivial morphisms. And this time, principal G2 bundles over an object of the two category will form a two category. So we have morphisms and two cells between them. And before we saw that principal bundles are closed under pullbacks, and in this two categorical context, this becomes that principal G2 bundles are closed under isocomma objects. So again, it is enough to replace pullbacks with isocomma objects, and everything still works. And so now we can also define the two-dimensional analogs of quotient prestacks. So this time, these objects will be three homomorphisms because they are morphisms between three categories, because two-cat is a three category. And they are defined exactly in the same way. So an object gets sent to the two category of principal G2 bundles over it, equipped with a morphism to the fixed object X. And then for every morphism F, the action on the morphism is defined this time via isocomma object. And since the isocomma object also has a two-dimensional universal property, this allows us to define the image of a two cell as well. And this object, again, is well defined, and one can prove that it is a three homomorphism. There is a bit of work to be done, but everything works. And now I wanted to see whether this object satisfies some gluing conditions as well, so some stacky conditions. But the problem was that there was no notion of higher dimensional stack suitable for this kind of three homomorphism. There were notions around, but they were just for the case in which, for example, here we have, as domain, we have one category, or other different cases, but none of them was suitable for this object. And so I introduced a new notion of two-stack. And the idea is that instead of generalizing the usual definition of stack, I generalized the characterization given by strip. And the reason for this, I hope will be clear in some minutes. So first of all, it was very easy to generalize the characterization, because we can just say that a three homomorphism of this kind is a two-stack if for every bisieve, the pseudo-functor of precomposition with the bisieve is a bi-equivalence. So we are just replacing the equivalences we had in dimension 1 with bi-equivalences here. So this is a very natural generalization. But the problem with this definition is that it is very implicit and abstract. And if one wants to prove that something is a two-stack using this definition, this is going to be a nightmare because we need to deal with these three categorical objects on the right-hand side, and it's very complicated to do so. And so I proved that there are gluing conditions that are more explicit and similar to the ones that we have for stacks, also for two stacks. And the idea to find these gluing conditions is, again, to use the Yoneda lemma, as it is done for stacks. So we are lucky that we have a three-categorical version of the Yoneda lemma that has been proved by Bounet, and it just says the exactly same thing of the Yoneda lemma. But here instead we have a biequivalence instead of an equivalence of categories. And also the assignment of this biequivalence is exactly the same that we all know for dimension 1. So given an object in f of c, this corresponds to a transformation whose component sends a morphism f into f of x. So exactly the same thing that we have for the classical Yoneda lemma. And then we have an assignment on morphisms and on two cells. And so thanks to this biequivalence, we can rephrase our definition of two-stack a bit, saying that a triomomorphism is a two-stack if and only if for every covering bisieve, the pseudo-functor of precomposition with the bisieve precomposed with the biequivalence given by the Yoneda lemma is a biequivalence. And now the idea is that being a biequivalence means these three conditions. So it is surjective on equivalence classes of objects, essentially surjective on morphisms, and fully faithful on two sets. And these three conditions will give us the explicit gluing conditions that we are looking for a two-stack, exactly as it happened in the case of stacks for the characterization. And so let's look at the conditions that we find. The third condition on two cells says that F is a sheaf on two cells. And this is what we were expecting to find because a stack is a sheaf on morphisms. So we were expecting to find that the two-stack needs to be a sheaf on two cells instead. And we are happy because this is exactly the condition that we find for two cells using the fully faithfulness condition for the biequivalence we have. Then for morphisms, we find that every descent datum on morphisms is effective. And again, this is the condition we wanted to find because for a stack, we have that every descent datum on objects is effective. So for a two-stack, this needs to happen for morphisms. And then we have a gluing condition for objects that is the new condition, the one that we didn't know how to find. And we didn't know what to expect. And I call this condition every weak descent datum is weakly effective. And I'm not showing you the details of the definition of weak descent datum and weakly effectiveness, but essentially the idea is that this time the global object recover the local ones only up to equivalence instead of isomorphism. And again, the notion of descent datum involves equivalences instead of isomorphisms. And these equivalences need to be coherent, need to satisfy some compatibility conditions with respect to composition and identities. So the notion becomes a bit more complicated, but the basic idea is that we are replacing isomorphisms with equivalences and a commutative diagram diagrams with coherent two cells, essentially. And so this is the result. So these are the explicit conditions that we can check when we want to prove that something is a two-stack. The problem with finding a definition of two-stack from the start in terms of explicit conditions was that we didn't know what were the right coherencies to ask for example, these condition on objects. So we didn't know what was the right notion of weak descent datum that we wanted to add. And the idea is that our implicit and abstract definition guided us in finding the exact right coherencies to ask. And now the result that we have is that if the 2-1 category is nice enough and the hypotheses that we ask are exactly the same that we had in dimension 1, but for dimension 2, so this is exactly the same result. And if the topology is subcanonical, and subcanonical in this two-dimensional context means that the representables are stacks, so two-dimensional sheaves, then X over G is a two-stack, according to our notion of two-stack. And again, there are different ideas behind the proof, but the most important one is that also in this two-dimensional context, we can express the objects of a subcanonical bisite as some kind of co-limits of the bisieves over them. And the right kind of colimit is a sigma bicolimit, so a particular kind of two-dimensional colimit, but we still have this possibility to express the objects as colimits, and this is what makes the proof work. And so these are the papers that contain everything I spoke about today. And this is everything I wanted to say. So thank you very much for listening.
What would be the next step, Elena, in this direction?
Yeah, so the motivating idea behind this is that, as I said, the classical quotient stacks are linked to cohomology theories. In particular, the classifying stacks allows to compute cohomology groups. And so the idea is that these generalized quotient stacks, and in particular the generalized classifying stacks that are obtained when X is the terminal object in the category, will allow to compute different kinds of cohomology. For example, stack cohomology or cohomology with coefficients in sheaves and things like that. So the idea is that we can use this theory to compute cohomology. And so I hope to work about this in the future, together with my supervisor, Frank Neumann.
And what would be the key examples? So the classical theory comes from algebraic geometry, right?
Yes.
So here, what would be the examples to have in mind?
So first of all, one can there are a lot of categories involved in different kind of geometry, so algebraic geometry, symplectic geometry, differential geometry, and so on, that are still categories of topological spaces, but with more structures. And the idea is that we can apply this theory to all these contexts, and so we get results that are speaking about those categories. So So the extra structure is given for free using these results. So this was the starting idea.
So, okay, hi Elena, Bruce Bartlett's here. Okay, can you hear me?
Yes, quite well.
Okay, good to meet you, hey?
Good to meet you too.
Okay. Frank is coming soon.
Yes.
Hopefully. Yeah. Are you coming as well? I mean to the AIMS conference.
No, I'm not coming.
Okay.
When is it?
2 weeks time. What is your specific? Do you have a specific motivating example for these generalized principal bundles and stuff?
The motivation didn't come from an example, but it came from the idea of computing cohomology for stacks. So for example, the notion of principal bundle was designed to make the computation for cohomology works. That's the idea.
But do you have some specific mathematical structure that you want to calculate the cohomology of that this technology will be useful for?
Yes, for algebraic stacks.
Which algebraic stack do you have in mind? Or
Any kind of algebraic stack.
okay. Is there not currently technology to calculate the cohomology of an algebraic stack?
There is, but first of all, it is computed as a cohomology group, while with this technology we could compute it as a two group. So we'll have more structure. And also, as the stack is a two-dimensional object in nature, it is natural to think that it should have a two-dimensional cohomology group instead of a one-dimensional one.
Okay, but so you're saying the current technology only produces one-dimensional groups, doesn't produce really?
Yes.
Even in the homotopy theory, like surely like in Lurie's work and that they would produce like higher groups?
I'm not sure whether I know that for classical stacks it just produces cohomology groups, but
okay.
But I think Frank is much more expert than me about these applications to algebraic geometry, so I think it will be able to answer the question much better.
Okay. Thanks.
At some point, you had a condition that pullbacks preserve colimits, right?
Yes.
I might have missed it. What happens to this condition in the more general framework?
It is that isocom objects preserve bicolimits. So exactly the same condition, but
do you have an idea of in which categories this would be true? What would be examples of categories where just that condition is true?
Yes, for any Grothendieck topos is true, and it's slightly more general than this.
But for Grothendieck topos, the old condition is true, right? It's a one category.
You mean the two-dimensional one?
Yes.
Yeah. So it should be true for every two-dimensional Grothendieck topos. So every category of stacks. for example.
You said it's true, so it's not something you checked yet.
No, I didn't.
Okay.
But also two-dimensional toposes are not so studied for now, so.
I have a very simple question.
Yes.
Right at the beginning, when we define a principal bundle with an internal group, do we require some compatibility with the internal group and the Grothendieck topology?
No, we don't. It's just an internal group. So that there is no compatibility.
Okay. In the classical case, I think you require it to be like a topological group.
What? Sorry? Oh, you mean because the topological group respects the yeah. I see what you mean, but we don't have this condition in this general framework.
But that's just because it's an internal group, right? Okay. Like a topological group, so group internal to topological spaces. So,
yes,
it's object in the category.
Yes, but in the case of topological groups, we have that the topology is the real topology of the topological space, and also the topological group respects this topology. So I get the question, but I think this is just a coincidence that they are the same in the category of topological spaces, but in general, it's not.
Okay.
And Elena, do you know the work of Mathieu Anel? Have you seen his stuff? Because he seems to work on similar things.
Oh, okay. I've heard of him, but I've never read anything similar to this. I'll check.
I'm sure what you're doing is different, but I would just like to know sort of like the relationship between what he does and what you do. Yeah.
I see. I don't know.
Okay. I'll send you an email.
Okay, thank you.
Yeah.
People online. I don't see anything in the chat. Yeah, I guess it's here to come up.
I will stop sharing my screen. Oh, okay.
Nobody online has any questions? Okay. Thank you very much for the talk.
Thank you.
That's very interesting.
Thank you very much indeed.
Thanks, Elena. Yeah.
So,
Thanks.